Hello everybody, and welcome to our webinar. And the topic of our webinar is structure-activity relationship analysis using MolSoft ICM Chemist. My name is Eugene Raush and I'm principal software developer here at MolSoft. So this webinar will conclude our Chem Informatics series of webinars which were hosted last few months. So the outline will be the following. So we will start with classical 2D SR analysis, which starts with R group decomposition by scaffold, and then we'll generate SR table and SR plot, and we'll discuss the advantages and representation of both of these approaches. The next we'll switch to activity cliff analysis, so SR landscape analysis, and I'll show you two methods of doing that kind of analysis. And we'll start with classical matched pair, and also we'll consider another way. It's structure activity landscape analysis SALI method, which was developed by John Van Drie a few years ago. And the last topic will be Bioisotere search, and I'll show you how to do the group replacement and linker replacement in your chemical space. So let's start with SR analysis. So this slide, I'm going to show you briefly this slide, and then we'll switch to the live demo of this functionality. So on this slide, it shows you the typical workflow, how you start. So you start with a spreadsheet with activities. Then optionally you can do some scaffold search or some other filtering by your subset, but this step is optional. So next we will do the R group decomposition. For R group decomposition, we will need to draw our scaffold, and after it's done, we'll end up with R group spreadsheet, which will contain multiple columns with R groups and original compounds and some other properties. So this is our result of the R group decomposition. So using this result, we'll go into two ways how to represent this data in an ICM Chemist. So the first one will be SR table, and the second one will be SR plot. So basically it's two ways of how to present your SR analysis results. So let me switch to ICM Chemist. All right, so let's start with by loading some spreadsheet with activities. So I will show you this COX-2 inhibitors spreadsheet. It contains multiple compounds, about 300. It's not about. It's exactly 320 rows. And as you see, there are multiple scaffolds in this spreadsheet. So we will use actually this one. So what you can do? So basically, all SR tools are grouped into this submenu: chemistry SR analysis. So the first one is R group decomposition. So here it offers you a few possibilities. You can either draw scaffold here by clicking this button, or you can choose a table spreadsheet with a scaffold, or use a text scaffold. So usually I prefer to have a scaffold as a separate spreadsheet. So in that case, it will be saved with your project, and you can modify it. So let's first draw the scaffold. So for that, we go here and click on to Open Molecular Editor. It should bring you this window, which many of you may be familiar with. It's pretty standard chemical editing tool where you can use different elements to draw your scaffold. So for our case, I will draw scaffolds like this. So for R group, I can if I want to specify R group on that point, so I just right click and say element and then, for example, R2. Or I can just press the number. For example, if I highlight this point and press number 1, it will be 1, or 3, it will be 3. So it's just a shortcut. You can join other. So here basically you may, there are two options. So either you want to terminate these positions or you allow some variations. We'll do both approaches, so I can show you how to do this so allowing variations or not. So to block anything in that position, you can right click and say connectivity as drawn, or you can specify connectivity 2. So that means only 2 heavy attachments are allowed, and there are already 2, so nothing except hydrogen can be here. So no, you don't want any variations in that position. So, but in our case, we just allow some variations. So that's how our scaffold will look like. So next step is to save that scaffold into some new spreadsheet. For that purpose, we just click on this append molecule to a chemical table, and usually we need to specify some names. So let's do it like this. So that will create a new chemical spreadsheet. So we have 2 right now. So first is our original one, and the second, it basically, you see it detects that it contains a scaffold, so basically the icon is a little bit different than for the just normal spreadsheet. So that's our scaffold. Now we can return to the chemistry menu and go to our group decomposition. Then we can choose this option. So choose a table with a scaffold. So our table is this, and the indexes actually specify the row number, because the table actually may contain multiple scaffolds, but in our case it's only single row, so 1 is okay. Then we select our main table, so which we will use for decomposition, and there are some options. So basically everything can be default except maybe you this option is interesting. So as you can see, we drew only 2 R groups in our scaffold, but we may want maybe that the program will auto detect some other variations around. So if we leave this option, the result table will may contain more than 2 R groups in the result spreadsheet. So let's keep these options and see what it will bring us. So just click OK, and this is our result. So basically, what happened? In addition to our original 2 R groups, the program found two more variations in 2 remaining positions. So it's R3 and R4. So and all the other columns from the inherited from the original table. So now we have 3 spreadsheets. So this is our original table, it stays untouched. We have our scaffold, and we have our decomposition table, which basically contains all the original data plus our group columns from decomposition. And also, if you click on this hammer button, you will see the scaffold which was used. So basically the scaffold was modified, as you can see. So it created two more R point variations on it. So basically that scaffold lives with the table, so you can always see how this table was, which scaffold was used to in our group decomposition for that particular table. So now the next step is to basically visualize that data so you can analyze this. Let's go again to this SR analysis and say generate SR table. So here it brings us with this kind of dialog. So we need to select two columns because they are for 2D ASR. It calls 2D because it basically allows you to look at the two R groups and the variation of these R groups at once. So you need to select two columns. And the question is, well, which column do you need to select? You can try different things, but we have this suggested pair box here, and you can click on calculate pair, and it shows that R1 and R4 gives you the more variations. But you can pick any of the combination of R2, R4, but suggested one is R1, R4. So let's select them. So to select multiple columns, I'm holding Control button and just clicking on these two columns. Then we want to color by activity. And also the nice option is to sort. If you choose sort, I will choose reverse because I want to grade activity be on the top, depending on what units are you measure. I mean what sort order do you want to receive. So sorting basically brings all the higher activity or lower if you choose reverse into left top corner, so you can see we'll see them more clearly. So if we click OK. So we'll see this kind of data. So it shows you R groups on the top and these rows and columns, and it also in every cell it may show you one or more compounds. It may show more than because you have not only if you would have only two R groups, it will always be one compound. But since we have more than two R groups variations, so it may be end up with multiple entries in a single cell. In that case, they are just drawn side by side, and they are colored by activity. So the rainbow of the coloring shows here. So basically it goes from red to blue. So what you can do with this table, you can arrange them side by side by double clicking, and then you can actually go to the click on these compounds and refer to the original tables for maybe for some other properties or other way to analyze. So this, for example, you can go sequentially click by them. And so the table is pretty sparse, so you can browse through it and make some conclusions about structure-activity relationship using this type of visualization. That was the first way of represent your data, and the second one. The second one is going to be, and I see already see some questions. I will answer them. So does this suggested pair feature? Yes, suggested pair maximize the filling of the R group. Yes, it basically it detects the pair which produce the more variations. So the produce less sparse table. Another way to represent the same data is to use our standard plotting functionality, which is located here in this icon. So it brings this dialog. So you can just select X will be R1, R4. So here it's an interesting option which allows you to jitter because as we already saw that we may have multiple compounds in the single point. So in a spreadsheet before they were arranged like side by side, but here in the plotting we can jitter them a little bit around the center. So it allows us to click on them individually. We may use color by activity, and there is a standard rainbow. So that basically it's a good start. So let's see what it produced. So that it produced this kind of plot. So where you can go and, for example, select some point or You can select it in the table, and you will see that selection is propagated. You can select multiple rows, and you will see that selection is also propagated. So what can we do with this plot? So let's return to the options dialog, and let's label some points. So let's do this. We want to show the structure as a label, but if we just press OK, it will be too crowded because every point will have some structures. And usually you sometimes want to show some interesting, only a few interesting points with the structure. In that case, this checkbox allows you to show labels or structures, in our case, for selection only. So let's do this. So nothing happened because we don't have anything selected. But once we select something, it produces this kind of chemical drawing, and you can drag it by just dragging the mouse. And if you right-click, not right-click, sorry, if you click a control key and mouse wheel, it allows you to zoom it and zoom out. For example, you can arrange it like that. And holding control, you can select a few more points. For example, you're interested in this one, and plus this one. So these are compounds which you think might be interesting. So for example, now you can create export it as a picture and put it into some presentation. And these positions will be saved. So if you clear a selection, they disappear, but if you select it again, it remembers the position. So basically, so once you arrange it, it will show you next time where it was, where did you put it last time. And another interesting thing you can do in options dialog, you can actually have a balloon. When you mouse over, you can it will show you the structure. For that case, you can just specify more column or comma separated list of columns with some other properties. For example, so let's just do one, and if we click on it, not click, just mouse over, and it will show you compound. So you can basically examine it like that. So just point your mouse and wait a little bit to pop up the structure. So that, and all other zoom, you can zoom using this mouse on axis. So basically everything else is pretty much standard. It's a standard plot which you can use with not only this kind of table, but with any other spreadsheet you have in ICM Chemist. So that's pretty much concludes the topic about 2D ASR analysis, and now we can switch to the activity cliff analysis. So let's get rid of these tables, and let's again open this COX inhibitor table. Let me read some questions. Can we organize a group? Yeah, I will probably answer them later because it may take some time. So we'll go through questions, and I will either email or answer them online. So let's switch to the cliff analysis. So there are two tools we provide to so basically, activity cliff analysis and is when you want to see small structural changes which lead to big activity changes. It can be either increasing activity or dropping activity, but in any case, some small variations in the structure will lead to the big activity cliff. We provide two tools to do that. And again, all you need is just a table with your activities. For example, this is COX-2 inhibitors. So to use this tool, you go to SR analysis, and let's start with generate SALI table. So structure activity landscape index, that stands for. This method was, I mentioned, was developed by John Van Dree and his group, and this is a PubMed reference for that publications. It used chemical similarity measure to produce sort of index which you can all use to sort your result table and see what changes produce larger activity cliffs. So basically, in most cases, you can just click OK. So in our case, that's fine. So we just click OK, and so you will see that the result table looks like this. So it contains two compounds from our original table with some variation. For example, here you can see that this fluorine is shifted from one position to another. And it produced the activity 1 and activity 2, and the SALI index, which basically the greater the number, the bigger activity change with respect to smaller structure change is received. So a sort of combination. So it's minimize, try to find the minimum structural change, and but in the same way it tries to maximize the activity cliff. So and the table is already sorted. So the first row is basically the greatest SALI index in that table, and you see that fluorine is shifted. So you can go and analyze other positions. So here you can see that there are not single point. It's basically single, so there are some switches here. So you can go, and this plot basically what it shows you, the size and the color represent the color by SALI index. So the bigger and more red, it basically shows a bigger cliff. So you can see maybe. So some people like to see it on a plot. But again, the table is sorted, so you can immediately see which cliffs you have in your data. So this method, since it's based on the chemical distance, it may produce the pair with more than one variation, or it can be not a single point variation, or it can be some other. So basically, it doesn't provide any common, does not guarantee that they have a big common scaffold. That's what I'm trying to say. And but the advantage of this method is that it's pretty quick. So it basically for the large data set, I would always recommend to start with this method, and if you found something, you may go to another method, which is molecular matched pair analysis, which produce always single point mutation, but it's slower than this SALI approach. But so let's on that point we can switch to another method, which is molecular matched pair analysis. So we go to the same SR analysis menu, and we select matched pair analysis. So basically, it's the same, similar dialog. You select activity column, and so this parameter, in most cases the default is good enough. You may decrease or increase it, but we not go into the details. So this is a technical parameter, so you don't want maybe change it in 99%. This parameter you may change, so this basically shows you how big R group you want to get in the end. So the limit on the R group size. So if you want only smaller groups, you may decrease this number, and you also may filter some R groups. But by default, everything will be included. So you can just click OK. And it starts, this method, as you see, it's much slower than SALI analysis, but it will produce, like for that data set, it will take like, I don't know, maybe 5 minutes. So I have already results in, let me bring another window with the results. So basically what it does, it gives you the similar look let me a little bit rearrange it. Yeah. Okay, so similar to SALI analysis, it produced the pairs of compounds, but here it also shows the variation, because this tool uses the common scaffold for this pair. So basically, it will show you that for example, here hydrogen was replaced by methyl, and the delta activity was 4 points. So it's pretty big clip, and you can see these compounds on a plot. So here the plot is looks like this, because the left activity is always less than the right one. So here they are all ordered. So that's why it only goes into upper portion of the plot. So also here you can actually visualize the scaffold. So if you go like this, so it will show you the scaffold, common scaffold for this pair. So this is again, this is very similar to SALI analysis, but here you always have the common scaffold and single point mutation variation, I would say, on that scaffold. So these two methods allows you to perform cliff analysis on your input data set. All right, let's switch to another topic. So again, I will probably answer questions. It's easy to answer them after the webinar. So thank you for asking. And let me quickly look at it. Yes, distance in the first method, in SALI method, the distance is chemical Tanimoto similarity based on chemical fingerprints. Can we use spreadsheet of activity in QSR? Well, yes. What do you mean spreadsheet? You always start with spreadsheet of activity, and if you have it if you mean some spreadsheet from Microsoft Excel, yes, you can export Microsoft Excel spreadsheet into ICM and then perform this analysis. Okay, so the next topic is related. It's not exactly structure-activity relationship, but it's related to this point. So let me show you this. So basically, that was a slide for we just walked through activity analysis, and another topic is bioisotere group replacement. That allows you to just search for some chemistry which has the similar activity in some assays. So let me briefly describe how we build our database. So we performed matched pair analysis on a Campbell activity data. So we ended up with 1.5 million of pairs and 27K of unique R groups. So in that analysis, we looked for the some single point variation in which leads to similar activity in some assay, or one or two more assays. So we built this database. It actually ships with ICM Chemist, so you don't need to download anything. So the file is in the distribution. So once you have ICM Chemist, you already have this database. So using this database, it basically what we do, we search this database for possible substitutions. So if you select some group, for example, you select some carboxylic acid, and run a search, it goes through the database, find the possible substitutions, and scores them by multiple parameters. So it goes so-called MPO, multiple parameter optimization. For in our case, there are a few parameters, selectivity and specificity. So selectivity means that the activity change was lower than some certain, so the lower activity change, the more selective this substitution was, and specificity is in how many assays we saw this particular substitution. And also there are some physical properties for hydrogen bond donor, acceptor, and a volume, which is basically important. So you want similar volume in your substitution. So this will be like your result spreadsheet for the substitution. So let's do some demo, and for that I will just open some file. And so for that, so let's see, let's start with a classical example of substitution carboxylic acid. So we right click on the so that method, it works only with one compound. So you just want to select one compound, select a group, and then run the possible substitutions. So here we right click on our compound, go to chemistry, and the last is find Bioisotere for the current group. So it brings you this editor where you can just select your group, for example here, and just press OK. It usually takes a few seconds to produce you this kind of spreadsheet. So the first row is always the original group, and the other rows provide you the possible variation. They're all sorted by Bioisotere distance, so which basically the combination of these multiple parameters score. So as you can see, the first hit is classical Bioisotere for carboxylic, and you can go further. And if you double click on that row, it will show you the data. So it go inside that data and show you the original Campbell data for that particular substitution. So you can basically analyze what was done here. So every double click will bring you these examples of original Campbell data. So what we can do, we can also try to find some, let's see what substitutions we can do. So here, for example, it suggests for what you can substitute for this. So this kind of chemistry. So basically, this type of analysis you can perform on any chemical data you have. Like you load any spreadsheets and you just try to find some substitution for your group. So this was our group substitution, but also this database which I was talking about, this Campbell database we compiled from the Campbell activity, it also contains the linker substitutions. So you can actually not only substitute our group, but you can try to find the new linkers for your compound. So it's actually very similar. So you go to your compound, find Bioisotere, and here you can select something with two points. For example, this peptide type bond. You want to find some substituent for that. So it gives you this kind of spreadsheet where you can analyze your. And for the linker, it also the distance, the minimum number of bonds in your original, comparing to your original linker. So because for the linker, you're not only interested in volume, but also how far these 2 points are. So it gives you the same similar spreadsheet with multiple parameter optimization components, and you can also go through it and analyze this data. And I think in the, let me show you, let me check if I have anything Yeah, so this slide is for linker, so we have a little bit less pairs of linker. It's only 500,000 and 47K of unique linker substitutions. And here it's the information how we obtain. This is the same Campbell activity data, so but only in that case we analyze linkers and not single R groups. Well, I think that's pretty much it. So I will go through questions right now and see what I can answer right now and what can be. So are you very only from single connection? Well, yeah, this question I probably answer. So not every scaffold, but two R point scaffold. So 3 R points are not supported. So you have to select a scaffold with 2 attachments. That was the question. The Bioisotere only support single point connection, or you can use the scaffold. Do the examples of Bioisotere include the number of examples where a structural pair does change the activity? Our database contains everything. I mean, we didn't filter our database for any particular. When we search, we look for small activity change, but we can obtain groups with a big activity change, but we need to change. I mean, it's all scripted in the macro, so we can just flip the condition, and it will give you the pairs with a big activity change. So information is in the database. Okay, so that's, I think we answer. Can we get QSR model equation? I need to check that. I'm currently not sure, but it probably can be done. So I will get back with these questions. So okay, I think we're done. So thank you very much for attending. I will follow up again with your questions, the one which I didn't answer, by email. So thank you, and hope you enjoyed our webinar.